As humans kind of move to explore space a little bit more and exit our home planet of Earth, one of our first places that we want to explore is Mars. Mars is a bit of a tricky destination for us. There's a lot of high radiation on Mars' surface. Temperatures on Mars can change drastically. In order to set up a human base on Mars, we really need to mitigate these temperature changes and the radiation. One of the possibilities of doing this is within Martian lava tubes.
So Martian lava tubes are one of the places that are the most promising for human settlement on Mars. So there's a few things that we want to do when we're exploring them. First, we want to actually figure out what they look like. This will give us an idea of if these are even places that we can build a settlement, how we'll need to adapt them. But we also want to see if they're livable.
So our concept of operations is really divided into 3 different sections. Our first stage is launch. So we're launching from Earth and going to Mars. That's really the gist of that stage. The second stage of our concept of operations is our descent into Mars. So we have a parachute that deploys to slow our entry speeds. And then we have a solar balloon that will be inflating as we fall to really slow down those speeds until we reach the surface where we will land softly. And then this third stage is the most important, and this is the lava tube exploration phase. Our solar balloon will hover over the skylight entrance of the lava tube, and it will lower an inflatable rover into the lava tube. At this time, the rover will be collecting data of the entrance with a camera and LiDAR, and then it will lower all the way to the bottom where it will touch down on what we suspect to be rough surface as it's caved in from the skylight entrance. The rover will then proceed to explore the lava tube. So we're looking at around 500 meters to explore. Every 83 meters, it will drop an antenna. The antenna will relay data back to Earth so that it can be analyzed. But because of the lava tubes, we want to make sure that no data is lost.
Underground wireless connection is very problematic due to the very conductive walls, absorbing the RF waves, and multipath fading. Multipath fading is a phenomenon where one transmitter will send a signal, it bounces off objects and goes to the receiver at different times, and it creates errors in the data or communication. And the way to mitigate that is through circular polarization, and the antenna I picked to do that is a dipole helical antenna.
The Martian surface has a series of prevailing wind currents. They generally travel in the same types of patterns, and by selecting both our landing region and the area that we wanted to study, we sort of charted a path that went with the wind so that we could harness that for our propulsion. So we land at the Noctis landing site, and then there's a nice little current of wind that will take the solar balloon almost directly to the RCMON site, which is where most of the lava tubes in that area are.
One of the unique aspects of our system is that it travels on Mars a lot quicker than current rovers and explorers do on Mars. They a lot of times require direct supervision from Earth, which usually means that those systems are really, really slow. What our system does is it travels over 1,400 kilometers, which is basically unheard of for any current Martian explorers. And we're doing this all because it's a fully autonomous system.
We have cameras and 3D LiDAR in order to map the entire cave. And we also have a temperature sensor and a rad to make sure that the caves themselves have a habitable temperature and they're not going to poison us with radiation.
So we've taken our prototype to kind of give a model of our mission. The prototype is what's going to bring us to technology readiness level 3. This is just validating the mission concept. We want to make sure that this is a viable mission before we proceed to more scalable testing.
The prototype concept of operations consists of an octocopter drone, which lowers a rover. This rover goes down on an elevator system, and once it reaches the bottom, it can disembark and then explore a mock lava tube.
It's not very feasible to actually create a solar balloon on Earth because of a very high atmospheric pressure in comparison to Mars. So we decided to use a drone just to mimic the lift that is generated and also to test our other systems. So with our drone, we will be lowering the rover through an elevator system, which is very representative of our theoretical model on Mars. And then with our prototype rover, while that's not necessarily a replica of our theoretical design, it's mainly just being used as a transportation tool to test all of our instruments.
Because our project is so large, we can't have a full suite of instrumentation like we originally would like. But the main goal of the prototype is to test to make sure these systems would function together. So rather than having a 3D LiDAR, which is significantly more expensive, has significantly higher data rates, which would add a lot of complexity to our communication systems and increase our power consumption. We scaled everything down to a 2D system so that we can prove that we can actually navigate with the map that we're creating, as well as create a very simplified map of some known environment. Having a smaller suite of instrumentation allows us to test our core systems without going over budget and without increasing the complexity beyond the timeline of this project's lifespan.
To enforce the relay system, we'll travel in different pipelines, and it'll go from the rover to the garage to the drone and to the ground station where the data can be analyzed.
Some of the main focus that we're trying to accomplish with this prototype is a lot of the software. So we want to make sure that we are autonomously navigating. We're doing this navigation without the use of GPS, as we won't find that on Mars. And then using algorithms to tie together the data that we find and really characterize the environments that we're testing in.
So the rover is going to be navigating using the LiDAR and IMUs. The IMUs are going to provide sort of a backup for the LiDAR, because the LiDAR sort of gives a map of the environment, right? And the IMUs serve as more of like you can integrate up the accelerations that you sense, and you're able to combine that using a Kalman filter, and you'll get a more accurate sense of your attitude.
Initial testing was done in the AME department. One of the labs there has a high room. It's netted off for drone usage. We did our initial test there just to make sure that the propellers worked, make sure the motors worked, make sure that the system was stable. Once that had been verified, we took the entire system out to Christopher Columbus Park. It was a UAV, UAS designated area nearby. We were able to fly it there and have the drone fully take off, ensure that that system worked. The aerial delivery system was capable of functioning. For design day, we've also constructed a mock lava tube, which the rover will be able to explore on its own, generate a point map, and prove that that's functional.
The rover was tested in Pepper Sauce Cave to kind of mimic the lava tube environment. And so that gave us a good idea of how the rover would act in a real life scenario. This is especially useful because the LiDAR is 2D, and ideally in our theoretical prototype, we'd have a 3D LiDAR. But still, the challenges faced in getting the rover to navigate through through the Pepper Sauce Cave still apply to the 3D LiDAR.
My name is Elijah Greenfield. I am the propulsion and mobility lead for Project Sparrow.
My name is Andrew Frisch. I'm the structures lead of Team Sparrow.
My name is Roman Anthis. I'm the guidance, navigation, and control lead for Sparrow.
I'm Kyler Neitzel, power communication lead for Project Sparrow.
My name is Nick Mamana. I am the instrumentation lead for Team Sparrow.
My name is Anna Dinkle. I am the systems lead and project lead for Project Sparrow.